Hi, my name is Johan Tekel. Welcome back to our tutorial series for internal forces. I'm not sure if I'm gonna do this for every episode of this tutorial series, but yeah, let's show again what internal forces actually are. So when we have a beam, we can cut through that beam to find out which forces reside inside, as the name already says, internal forces, right? Um, we have the normal forces shown here in green with N. Those are basically tensile forces or compressive forces. Tensile forces are positive normal forces and compression forces are negative normal forces. We also have shear forces shown here in red. The Q is for Querkraft, that's in German. And yeah, they are positive in the direction that are shown here and negative when they're applied the other way around. Now for bending moment, they're like positive in the directions, in the rotating directions that are shown here, and negative the other way around. I also had that kind of trick for bending moment, like I'm looking at the cut. For example, I imagine that I have water on the top of the beam that's like flowing in the direction of the cut, and the direction of the positive moment is the way I need to basically bend the beam so that the water is not gonna fall down. If you can picture what I just described, you're gonna see that the direction of the positive bending moments is pretty easy to determine. So normal forces when the beam is compressed should be negative, right? This beam here has an horizontal single load applied in the horizontal direction at the right roller support. It's compressing the beam. So we're going to have a negative normal force. On our graph here, that discontinued line you see is the positive side. So the positive side is below. When a function is positive, we're going to have a graph on the lower side. And when a function is negative, we're going to have a graph on the upper side. In this case, you see that the graph, the green line there, the green graph for the normal force, the constant value is above. So it's a negative value as expected because the bar we have there is compressed. For the shear forces here, I have a trick for this. I presented already in the previous videos. We're gonna look at our beam from the right to the left. Okay, we normally read from the left to the right. I mean, normally for an English-speaking person. I know there are other languages where reading from the right to the left is pretty the normal case, Japanese and stuff. So we're gonna read the beam here from the right to the left. So we look at the beam from the roller support, staying over there on the right, moving towards the pin support on the left. Okay, so when we are at the roller support, what's gonna happen? Every time that we have a load in a specific direction, we're gonna input a jump with the value of that load in our shear force distribution. The shear force distribution is what we have here in the middle, the two rectangles that we got there. So regarding our system, a simple supported beam with a single load applied in the middle in the vertical direction downwards. What's going to happen? The reaction forces of the supports are going to be half the value of that single load, okay, directed upwards. So on the left side at the pin support, we're going to have half the value of the single load directed upwards. And on the right side at the roller support, we're also going to have a value that's going to be half the value of the single load directed upwards. So what does that mean for our shear force distribution? From the right to the left, we have a jump, okay, upward, with the value half of the single load. And then in the middle, we have a jump downward because of the load itself, okay? So it goes downward. And you can see that the jump we had on the right was just half of the value, because now we have the full jump going downwards, and you see we now at we have the same value that we had on the left, okay? On the right, and the same jump, but on another side. Now it's constant. Why is it constant after every jump? In this case, it's because we don't have any distributed load in between, okay? It's constant going to the left. When we reach the pin support, we have a jump upward again. So it basically comes back to zero. Is what's basically always happening with the shear force. So that last jump is because of the reaction force at the pin support on the left. What we have here is now a distributed load on the same system, the same simple supported beam. Now what will happen with the distributed load is basically the same. We're still gonna have jumps when we have single loads, and when we have a distributed load still loads kind of. So we're still gonna move in the direction of the load, and the distributed load here is directed downward. So let's look at the system again. What's gonna happen? Our distributed load, we have a resultant force that's applied in the middle, and very similar to the case we had above. The resultant force is gonna be like this single load we had in the previous case. So the reaction forces of the supports are also gonna be half the value of that resultant force. Okay, so on the left here, we're gonna have a force applied upward with half the value of the resultant force. On the right side, at the roller support, we're gonna have the same force, basically the same magnitude, applied upward. Now, in our shear force distribution, what's gonna happen? We look at the beam again from the right to the left. So from the roller support moving towards the pin support, what's gonna happen? A jump upward caused by the reaction force at the roller support. Then we have a distributed load we need to take into consideration. Because of that constant distributed load, we're gonna have a linear distribution, or a linear change of the shear force. So it's moving linearly downward because the distributed load is directed downward, okay, up to the left of the beam, up to the pin support. And what happens at the pin support? A jump, again, jump back to zero. That jump is as big as the value of the reaction force at the pin support, and the value of the reaction force at the pin support is equal half of the resultant force of our distributed load. Now, bending moments. What happens here? For the bending moment, we also have a small trick. We look at our beam here. Again, the same system, with a single load applied in the middle. How will this beam deform? Now, this beam can deform in the following way. Look, this graph, the blue graph over here, the parabola. Okay, that's how that beam can deform. The blue graph over here is basically representing a bending moment for the distributed load case, but just follow me here. The beam over here with a single load can deform like the blue line, the last blue line here is showing a parabola. It's a quadratic function kind of. That's how it can deform. So the beam at the pin support on the left is not gonna move, so it stays to zero. The beam on the right side at the roller support is not gonna move downward either. It's zero. And in the middle, we're gonna have a deflection. And the whole form will look like this, like a parabola. Like I said, it's a nice curvature we have there. Now, what we're gonna do is that when we picture this beam, when we picture the way this beam deforms, we can imagine that the lower side here is gonna be under tension. So imagine you have your maybe a pen, and you try to bend it in this way. You can imagine that the lower side of the pen is more under tension than the upper side. The upper side might even be completely under compression, kind of. Another way to picture this is maybe to use your arm. When you have your arm, you can basically try to, what should I say, maybe stretch it. When you stretch your arm and you try to bend it downwards, kind of, you can feel which muscles are basically under tension and which others are under compression. It's always so that if the muscles above the biceps basically are under tension, when you stretch your arm, kind of, the muscles below are under compression. And if you do the other movement, now you're basically trying to bring your point kind of to your head, try to close the arm. What happens that now the biceps is under compression, and the the muscle below, I don't know exactly how it's called, I don't know if it's a triceps, I'm not sure, but the other muscle on the other side is under tension. So it's basically what's happening here. When you bend the beam, there's a side that's under compression and another side that's under tension. In this case here, the side that's under tension is the lower side, and the side that's under compression is the upper side. And our trick is to say that the moment, at least in the moment distribution, the moment is going to be on the side of the tension side. Okay, so that's actually the trick. I think it's the first time I do this part here, this introductory part, with so much information. So it's probably gonna be the last time I do this. Next time, for the next episodes of this tutorial series, I will just start with the exercises. So let's go and start the game, and I will give the explanations on the quick determination of internal forces. That's basically what we want to do here, because we're not writing stuff down. We're not calculating those forces by hand. We just want to look at the system and kind of like know how the internal force distribution is going to look like. Let's go. So here we ask for the shear forces. We have a cantilever beam with an inclined load on the free end. I mean, it's not a free end anymore since there's a load. The load is inclined, and it has a vertical component that's directed downward and an horizontal component that's directed to the left. The only thing that interests us here is the vertical component. So we look at the beam from the right to the left, and we're going to have a jump downwards, and then it's going to be constant, and the last jump is going to be upward at the reaction force. So this one is going to be the answer here on the right. On the middle is wrong, on the left is wrong. Bending moment is what's asked from us here. That's basically the example we had in the introductory explanations I was giving. So we know already that this case here on the left is wrong. This case here in the middle is wrong, and this case is right. I actually remember now that I didn't really talk about the answers from those cases. I just talked about the trick. So the bending side, the tensile side, is going to be below. And why do we have this distribution here? Because we don't have any distributor load, so it needs to be linear in between the values. That's basically the same system we just had. The only difference here is that the load was shifted in the vertical direction. When we're working with a system and we assume small deformations, and it's actually allowed to do this, to just shift a force along its action line. So we're going to have the exact answer as previously. In this case, the normal forces are asked. So actually we want to know if this beam is under compression or under tension. But what we see here is that the load is a vertical one. It's a linear changing vertical load, but it's still a vertical load. So the only thing we are going to have in those reports are vertical reaction forces, no horizontal force. And we could even do some of the forces here in the horizontal direction, and we would see that the horizontal force at the pin support on the left is going to be 0. So the moment distribution here, sorry, the normal for distribution is 0. Now, the shear forces is what's asked from us here. Which reaction forces are we going to have here? The single moment that's applied on this beam, once you turn the whole beam in the in the clockwise direction. And what are our reaction forces gonna do? They're gonna try to create a moment that acts in the opposite direction. So the support on the right, the roller support is going to have a force going upward, and the one on the left is going to have a force going downwards. And reading the beam from the right to the left, a jump up, constant, then jump down. That's here. Yeah, that one was the right one. Yeah, about this single moment applied on the beam. I said last time I would do an extra video about it. I haven't done it yet, but I thought about another trick, a new trick, not even the one I was using this for. So we're gonna look at the beam from the left going in the direction of that single moment. So from the left you have like a beam, a pin support, and we move towards that single moment. That single moment, it's turning clockwise, and that's the opposite direction of a positive moment, okay, on the positive face, okay. And we're gonna do a jump in the opposite direction, and that's gonna be didn't even have the time to do it.